Earth today is a vibrant, life-sustaining paradise, but it wasn't always this way. Before the age of dinosaurs, our planet was a hostile, barren landscape, far from the blue-green world we know today. But why did Earth look so terrible before the dinosaurs? In this video, we'll take you on a journey back in time to explore the harsh conditions of early Earth and understand how it transformed from a volcanic wasteland to a cradle of life. Let's dive into the dramatic events that set the stage for everything we know today. Imagine a world where Earth is nothing like the blue and green planet we know today. Instead, picture a landscape filled with raging volcanoes, searing hot lava, and a sky thick with toxic gases. This is what Earth looked like billions of years ago, long before the first dinosaurs roamed. But what if I told you that you might be an alien on this planet? The origins of life here are shrouded in mystery, and there's a fascinating hypothesis that life on Earth might have come from the stars. This idea is known as panspermia. It suggests that the building blocks of life, or even life itself, didn't originate here. Instead, it was carried across space, perhaps frozen on a piece of rock or encased in ice, traveling light years across the cosmos before crash landing on Earth. This means that our earliest ancestors could have hitched a ride on an asteroid or a comet. If this is true, it could completely change our understanding of life on Earth and our place in the universe. But before we explore this possibility, we need to go back even further to when Earth was just forming, a time when it was a terrifying, inhospitable place. Over 4.5 billion years ago, the solar system was a chaotic place. Instead of planets neatly orbiting the Sun, there were countless rocky fragments and massive protoplanets smashing into each other. Earth began as a swirling cloud of gas and dust, slowly coalescing through gravity. The young Earth, during what we call the Hadean era, was a vision of hell. Named after Hades, the Greek god of the underworld, this era was marked by extreme volcanic activity, searing temperatures, and an atmosphere filled with carbon dioxide, methane, and sulfur compounds. It was a toxic mix that would make it impossible for any of today's life forms to survive. The surface of early Earth was a roiling ocean of molten rock, constantly being bombarded by asteroids and comets. These impacts were not small. Some of the asteroids were as large as entire cities. This period of intense bombardment, known as the Late Heavy Bombardment, lasted hundreds of millions of years. One of these colossal impacts changed the course of Earth's history forever. About 4.5 billion years ago, a Mars-sized protoplanet named Theia collided with the young Earth. The collision was so violent that it ejected a massive amount of debris into space. Over time, this debris coalesced to form the Moon. The formation of the Moon had profound consequences for Earth. The Moon's gravitational pull stabilized Earth's axial tilt, which created consistent seasons and influenced ocean tides. Without this stabilizing effect, Earth might have wobbled wildly, causing unpredictable and extreme climate changes. The Moon also slowed down Earth's rotation, which initially had a day length of just 6 hours. The collision not only shaped the physical appearance of our planet, but also set up the conditions necessary for life to eventually take hold. After the surface cooled and solidified, Earth still looked nothing like it does today. Instead of oceans and continents, the surface was a cracked, barren wasteland with vast volcanic plains. The atmosphere was thick and filled with greenhouse gases, making it extremely hot and devoid of oxygen. Yet, this hellish environment was the stage for one of the most extraordinary events in the history of our planet: the emergence of life. Life on Earth began as tiny, simple molecules that combined in just the right way to form the first self-replicating structures. The exact mechanism of how life started is still debated by scientists, but it likely involved organic molecules that could interact with each other in a soup of chemicals. These molecules may have originated from Earth's own volcanic activity, or they might have arrived from outer space, brought here by comets and asteroids. This is where the panspermia hypothesis comes into play. Panspermia suggests that the seeds of life exist throughout the universe and can travel vast distances, surviving the harsh conditions of space. These microorganisms could endure the freezing temperatures, cosmic radiation, and vacuum of space by going into a dormant state. When an asteroid carrying these microscopic hitchhikers crashed into Earth, it might have brought with it the first signs of life. This idea is supported by the discovery of certain bacteria on Earth that can survive extreme environments, like the deep ocean hydrothermal vents or the dry, cold plains of Antarctica. These extremophiles suggest that life, once it begins, can thrive even in the most hostile conditions. The earliest life forms on Earth were simple and microscopic, resembling bacteria and archaea. Scientists believe that these organisms lived in extreme environments, such as deep-sea hydrothermal vents, where superheated water, rich in minerals, creates a perfect setting for chemical reactions. These vents, far from sunlight, provided a unique ecosystem driven by chemosynthesis, where bacteria could convert chemicals like hydrogen sulfide into energy. One of the oldest known life forms, called Luca, last universal common ancestor, is thought to have lived in these harsh environments. Luca is not a single organism, but rather a theoretical ancestor of all life on Earth, giving rise to the incredible diversity we see today. As life began to evolve, some of these early microorganisms developed the ability to photosynthesize. Cyanobacteria, among the first to use photosynthesis, harnessed sunlight to produce energy, releasing oxygen as a byproduct. This process was a game changer for Earth's atmosphere. Over millions of years, these tiny organisms created structures called stromatolites, which still exist today. Stromatolites are layered, rock-like formations made up of colonies of cyanobacteria, and they played a key role in slowly transforming the atmosphere from one dominated by carbon dioxide to one rich in oxygen. This shift, known as the Great Oxidation Event, was one of the most significant turning points in Earth's history. The increase in oxygen allowed for the evolution of more complex life forms. Organisms that could survive in this new oxygen-rich environment began to thrive, leading to the emergence of eukaryotes, cells with a nucleus and organelles like mitochondria. Eukaryotes were more efficient and complex than their bacterial predecessors, capable of forming multicellular organisms. This leap in complexity was made possible by a process called endosymbiosis, where a larger cell engulfed smaller, energy-producing bacteria. These engulfed bacteria eventually became organelles like mitochondria, which still exist in our cells today as powerhouses that generate energy. The appearance of eukaryotic cells marked the beginning of a new era in the evolution of life. With the ability to form more complex structures, these cells paved the way for the first multicellular organisms. Initially, life remained simple, with colonies of algae and other microorganisms forming the base of the ecosystem. But as time went on, the diversity of life began to increase dramatically. This explosion of diversity culminated in the Cambrian explosion, a period roughly 541 million years ago when most major animal groups first appeared in the fossil record. The Cambrian explosion saw the rise of complex multicellular organisms with specialized body parts and functions, including the first eyes and nervous systems. Before this, life was mostly limited to simple, soft-bodied organisms that left few traces behind. The Cambrian period changed everything, as the fossil record suddenly became rich with evidence of new life forms, including ancestors of modern animals like arthropods and mollusks. The evolution of multicellular life set the stage for an incredible diversity of organisms that would go on to dominate the seas, colonize land, and eventually give rise to the mighty dinosaurs. But before we get there, Earth had to endure billions of years of chaos, transformation, and cataclysmic events that shaped its surface and atmosphere, setting the stage for the next chapters of life's incredible journey. After the Cambrian explosion, The Earth entered a new era known as the Paleozoic, a time characterized by rapid diversification of life and significant changes to the planet's environments. This era, spanning over 290 million years, saw the rise of complex life forms both in the oceans and on land. At the start, marine life was teeming with a variety of strange creatures. Trilobites, armored arthropods with segmented bodies, became one of the dominant groups in the oceans. Their hard exoskeletons left behind an extensive fossil record, helping scientists understand what early marine ecosystems looked like. Alongside trilobites were brachiopods, coral-like organisms, and the first jawless fish, which marked the beginning of the vertebrate lineage. As the Paleozoic era progressed, life forms adapted to the different environments Earth provided. The first true fish began to evolve, including armored fish like placoderms, which had bony plates protecting their heads and bodies. This era also saw the emergence of the first sharks, whose adaptations made them effective predators. The oceans were bustling with an incredible variety of life, creating complex food webs and intricate ecosystems. However, the most groundbreaking evolutionary leap was yet to come: the colonization of land. While the oceans were thriving, life on land was still sparse. Early plants began to make the leap from water to land, evolving structures to cope with the challenges of a terrestrial environment. These early plants were small and simple, resembling mosses and liverworts. As they spread across the barren landscapes, they created the first primitive soils, setting the stage for more complex terrestrial ecosystems. Over time, plants developed vascular tissues, which allowed them to grow taller and transport water and nutrients more efficiently. This innovation led to the rise of the first forests, dominated by towering ferns, horsetails, and club mosses. With the establishment of plant life on land, new habitats opened up for animal species. The first to venture onto land were likely arthropods, such as millipede-like creatures and early insects. These pioneers fed on decaying plant matter, starting the first terrestrial food chains. Eventually, some fish developed the ability to breathe air and use their fins to move across land. These adaptations gave rise to the first amphibians, which could live both in water and on land, marking a critical step in the evolution of vertebrates. Amphibians flourished in the lush, swampy environments of the Carboniferous period, a time when Earth's atmosphere had extremely high levels of oxygen. This abundance of oxygen not only supported giant insects, like dragonflies with wingspans as wide as a modern eagle, but also allowed amphibians to grow to enormous sizes. However, amphibians were still dependent on water for reproduction, limiting their ability to fully conquer land. The evolutionary solution to this problem came with the development of the amniotic egg. The amniotic egg was a revolutionary adaptation, allowing early reptiles to lay their eggs on land without the risk of desiccation. Unlike amphibian eggs, which had to remain in water, the amniotic egg had a protective shell and membranes that retained moisture, providing a safe environment for the developing embryo. This adaptation gave reptiles a significant advantage, enabling them to colonize a wider range of habitats and become the dominant land vertebrates by the end of the Paleozoic era. But the triumph of early reptiles and the flourishing of life on Earth came to a sudden and devastating halt at the end of the Permian period, about 252 million years ago. This period marks the boundary between the Paleozoic and the Mesozoic eras and is known for the most catastrophic extinction event in Earth's history, the Permian extinction, often called the Great Dying. The causes of this mass extinction are still debated, but scientists believe it was triggered by a combination of volcanic eruptions, methane release, and possibly an asteroid impact. The volcanic activity in what is now Siberia was particularly intense, releasing vast amounts of lava and toxic gases into the atmosphere. This led to severe global warming, ocean acidification, and the depletion of oxygen in the seas, creating dead zones where most marine life could not survive. As a result, an estimated 90% of marine species and 70% of terrestrial species were wiped out. It took millions of years for life on Earth to recover from this devastation, but it set the stage for the rise of the dinosaurs in the following era. The Mesozoic era, often referred to as the Age of Dinosaurs, was a time of recovery, adaptation, and domination by these incredible reptiles. The Mesozoic is divided into three periods: the Triassic, Jurassic, and Cretaceous. The Triassic period began after the Permian extinction, with the survivors adapting to a warmer and more arid climate. Among the notable survivors were the archosaurs, a group of reptiles that would eventually give rise to the first dinosaurs. Early dinosaurs were relatively small and bipedal, but they quickly diversified into a wide range of forms. As the Jurassic period dawned, the climate became more humid, and the supercontinent Pangaea began to break apart, creating new coastlines and shallow seas. This shift in geography created new ecological niches, allowing dinosaurs to diversify even further. Massive herbivorous dinosaurs like Brachiosaurus and Diplodocus roamed the land, while predatory giants like Allosaurus and Spinosaurus became the apex predators. The first birds also appeared during this time, evolving from small, feathered theropod dinosaurs. Archaeopteryx, one of the earliest known birds, had both feathers and teeth, bridging the gap between dinosaurs and modern birds. The Cretaceous period was the last chapter of the Mesozoic era and saw the peak of dinosaur diversity. This period gave us some of the most iconic dinosaurs, including the Tyrannosaurus rex, Velociraptor, and Triceratops. Flowering plants, or angiosperms, began to dominate the plant world, creating lush environments that supported a complex web of life. However, the reign of the dinosaurs would come to a sudden end about 66 million years ago, when a massive asteroid struck the Yucatan Peninsula in present-day Mexico. The impact of the Chicxulub asteroid was catastrophic. The force of the collision sent shockwaves around the globe, triggering earthquakes, tsunamis, and wildfires. Dust and debris filled the atmosphere, blocking sunlight and causing a dramatic drop in temperatures. This event, known as the Cretaceous Paleogene (KPG) extinction, wiped out about 75% of all species on Earth, including most dinosaurs. The only dinosaurs to survive were small bird-like species, which would eventually evolve into the birds we see today. With the dinosaurs gone, the Cenozoic era began, marking the rise of mammals. These small, shrew-like creatures had lived in the shadow of dinosaurs, but now they had the opportunity to diversify and fill the ecological niches left vacant. Mammals evolved rapidly, giving rise to new forms including early primates, hoofed animals, and large herbivores. One of the most remarkable evolutionary stories of the Cenozoic era is that of the whales. These massive creatures evolved from land-dwelling mammals, adapting to life in the ocean over millions of years. On land, mammals continued to diversify, leading to the emergence of giant mammals like the woolly mammoth, saber-toothed cats, and ground sloths the size of modern elephants. Birds also thrived, filling many ecological roles once dominated by pterosaurs. The evolution of primates eventually led to the rise of humans, who developed advanced tools, language, and complex societies. Today, we live in the Anthropocene, a proposed geological epoch that marks the significant impact of human activity on the Earth's ecosystems and geology. Our species has transformed the planet in ways no other species has before, creating both challenges and opportunities for the future of life on Earth. The extinction of the dinosaurs was a pivotal moment that reshaped the course of evolution, allowing mammals and ultimately humans to become the dominant life forms on the planet. As we look to the future, the threat of asteroid impacts still looms. NASA's DART mission and other planetary defense projects aim to detect and deflect potentially hazardous asteroids, ensuring that humanity is prepared for a disaster like the one that ended the age of dinosaurs. By understanding Earth's deep history and the dramatic changes it has undergone, we gain insight into our own origins and the delicate balance that sustains life on this unique planet. While the dinosaurs are long gone, their legacy lives on in the birds we see today, the last living dinosaurs. They serve as a reminder of the incredible story of life on Earth and the constant evolution that has shaped our world. As we look ahead, the story of life continues to unfold, and it is up to us to ensure that the next chapter is a bright one for all living creatures.